There is another way of stating what Einstein realized, that in a freely falling lift gravity disappears, and that is the following. Now we know that on the surface of the earth, if you conduct experiments like dropping objects, all objects drop with a constant acceleration which is about 980 centimeters per second square. Now supposing your friend is in a spacecraft very far away, where in the neighborhood there are no massive objects, so that there is no gravity, then if the spacecraft accelerates upwards with an acceleration 980 centimeters per second square, if your friend does any experiments inside this accelerating frame, he will see that everything falls towards the bottom of the spacecraft with acceleration 980 centimeters per second square. If he holds the pendulum and releases the bob of the pendulum oscillates as though there is a gravitational force like Earth. In other words, a frame of reference, in the absence of gravitation, if it is accelerating upwards with some acceleration g, then it is as though the frame is not accelerating, instead there is a uniform gravitational force. In other words, these two frames are equivalent to each other. This is called the Einstein's equivalence principle. We'll have to go back by 2 slides. Right. And this whole idea that gravity can be made to disappear in a freely falling frame, or equivalently, if there is no gravity, if your frame is accelerating upwards, then you feel pressed to the ground, and is exactly that gravitational force. This realization, when Einstein got for the first time, he said that was the happiest day of my life. You have to go forward by 2 slides. Next slide. So in other words, if you have a frame which is accelerating upwards, then if you drop a ball with a horizontal velocity, because the frame is accelerating, so according to an observer in the frame, the ball will be going down, it will be covering a distance downwards by increasing amount, and therefore the ball will appear to take a parabolic trajectory inside the frame. This is exactly what happens when we throw a cricket ball on Earth and see the cricket ball taking a parabolic trajectory. The same thing should happen to light also. Einstein realized that if this is the case, then in an accelerating frame, if you shine a torch beam, then the light, just like the ball taking a parabolic curve, the light will also bend. And since Einstein's equivalence principle says that a uniformly accelerated frame is equivalent to a frame in uniform gravity, therefore Einstein could predict that light in a uniform gravity will also take a trajectory which gets bent. So the upshot of general theory of relativity, which is a relativistic theory of gravitation, is the following. According to Einstein's theory, gravity is not at all a force. The fact that we see on Earth that if we chuck a ball, the ball takes a parabolic trajectory, these trajectories, they might appear to us as curved trajectory, but in reality, these trajectories are the shortest possible distance in the geometry which has been distorted by massive objects. In other words, according to general theory of relativity, the geometry of the space-time is no longer Euclidean, rather the geometry is curved or non-Euclidean. And why has it got curved? Because the presence of energy and momentum carried by objects around us. So geometry is the key thing in general relativity, and gravity is nothing but the gravitational force is a manifestation of the geometry of the non-Euclidean space-time brought about by the presence of matter. So in other words, what Einstein is telling us is that if there is matter, the energy and momentum associated with the matter causes the geometry around it to be curved, while the curved geometry tells us how a test particle should move in a trajectory. In other words, the geometry tells us that a test particle in the absence of any other forces must take the shortest possible path. So general relativity tells us two things. One is the energy and momentum associated with matter causes curvature in the space-time geometry, while the curved space-time geometry tells that a test particle must follow the straightest possible path in the absence of any other forces. So as though the whole universe has been created on geometrical principles, and this picture painted by Blake, in his mind, he thought of God creating the whole universe using geometrical appearance, and therefore this picture is apt for general theory of relativity. What characterizes geometry in a four-dimensional space-time? Remember, when we talked about special theory of relativity, we found that the square of the proper distance is nothing but c square times square of the time interval minus dx square minus dy square minus dz square. In general theory of relativity, the whole thing gets generalized. Now, the square of the distance between two infinitesimally close events, ds square, is equal to g00 into dt square plus g11 into dx1 square, etc. That means there are essentially 10 functions gij which are called the metric tensor, and it is this metric tensor which tells us how to measure time and distance in a curved space-time. Of course, if you want to really learn general theory of relativity, you have to learn the mathematical language of tensor calculus to understand the nitty-gritty of general relativity. Here, in this 1 hour talk, and since I'm trying to only give a flavor of general theory of relativity, I want you to take back home the concept that it is the metric tensor which tells us how to measure the distance, which is the key element which describes the non-Euclidean geometry of the curved space-time. Go back to Euclidean geometry. In Euclidean geometry, the metric tensor is very trivial. It is just g00 will be 1, g11 will be 1, g22 will be 1. But when we have arbitrary curved space-time, we'll have 10 functions, the gij, 10 functions of space-time events. Now, what are the physical consequences of general theory of relativity? It has several physical consequences.